Good morning, class. I want to welcome us to Chemistry 121. The last time we met, in the last class, we were looking at valence shell electron pair repulsion theory. We were not able to finish the class, so I would build on what we have learned and move on from there. We are looking at the effect of double bond on the bond angle. We mentioned the fact that in this particular molecule, COCl2, you have an sp2 hybridization. There is a trigonal planar structure, and in that structure, you should have 120 in between the atoms. But because of the presence of this double bond, you have a repulsion of this. So that was where we stopped in the last class. So we'll move on from there in this present class. Now, if we want to examine shapes of molecules that have 6 electron groups or 5 electron groups, for instance, we have antimony pentafluoride and bromine pentafluoride. Now, if you look at antimony pentafluoride, antimony in this case has an sp3 dehybridization, so which is a trigonal bipyramidal structure. Trigonal bipyramidal structure. So you have the axia and the this is the Lewis representation, but this is the molecule geometry. And if you look at it, you have a trigonal bipyramidal. You have, this is the equatorial and this is the axial. You have fluorine positioned in that way, or you have each of them positioned as terminal atom along the equatorial and along the axial. As previously mentioned, within the equatorial or between the equatorial, you have angle 120, and on the axial, you have angle 90. But in the case of bromine pentafluoride, you have this to be the Lewis structure. And by the time you draw the Lewis structure, you will see that there is a lone pair. You will see that there is a lone pair. Now, the implication is that bromine is a 6-electron system, which means that it will be an octahedra. Bromine has 1, 2, 3, 4, 5, and this lone pair. So it's an octahedral structure, but a distorted octahedral structure, which is an AX5E. And in this case, octahedral structure is supposed to have the square planar part and the pyramidal part up and down. So in this case, you now have that as a lone pair, and this lone pair would repel the bonds. This bond is supposed to be 90 all through, but there's a repulsion of the bond, and that reduces it below 90. So we have 84.8 degrees to be the bond angle. Now, you can have situations where central atom is more than 1. You have the central atom that is more than 1. For instance, in this acetone, we have CH3, and CO double bond. This is the Lewis structure. So you have this is a central atom, this is a central atom, and this is a central atom. In each of these cases, there are different hybridization. This is sp3 hybridization, this is sp2 hybridization, and this sp3 hybridization. So in that case, this will be tetrahedra, this will be tetrahedra, and this will be a trigonal planar structure. So let's look at what we're talking about. So this is tetrahedra. This is tetrahedra. So the angle here is 109.5. The angle here will also be 109.5. So all this because they are tetrahedra. But this center one, because is an sp2 hybridization, it will be trigonal planar, and it should have 122. 120, 120 is supposed to be the bond angle, but because of the repulsion as a result of this double bond, this becomes 122, then there'll be 122 here. To make it 360, then you have 116. So you can see that in this case, we have different types of hybridization because we have different types of central atom. So you have tetrahedra that is an AX4. You have trigonal planar that is an AX3. Now, having established this, what are the results or the implication of molecules having shape? What are the implication of covalent bond being directional? The implication is that it affects what we call the molecular polarity of the molecule. What do we mean by that? Because of the arrangement of your bonds in space, it will affect the way molecule, the overall polarity of molecules. So the overall molecular polarity depends on both shape and bond polarity. Polarity of bond is introduced by difference in electronegativity. So if one atom that is the central atom has a different electronegativity from the terminal atom, there will be a polarization of the bond towards the more electronegative element. However, by the time we now look at the molecule as a whole, it is possible that the dipole moment of your molecule is either zero or has a value. If it is zero, the implication, and there is a there is electronegativity between the central atom and the terminal atom. The implication is that the shape of the molecule may have canceled out the dipole moment. We are going to look at specific examples to explain what I'm trying to teach here. So a molecule is polar if it contains one or more polar bonds. So once the bond is polarized, that molecule will be polar. However, it doesn't necessarily translate that when you have one or more polar bond, the overall molecular polarity would be a dipole moment that is of positive value. So the unit of dipole moment is dB, and we have the individual bond dipole not canceling out each other for us to have a positive value for our dipole moment. So two things, polarity of the bond and individual bond dipoles not canceling out each other. So let's look at typical example to illustrate what we're talking about. In the case of CO2, carbon monoxide, I give you an assignment on the Padlet, and I deliberately left this because I wanted to see something. Now, if you look at this molecule, in this molecule, you will see that carbon dioxide is a linear molecule. Some of you did not get that in the class quiz. It's a linear molecule. The bond between carbon and oxygen is polarized towards oxygen because oxygen has higher electronegativity than carbon. The electronegativity of oxygen is 3.5, that of carbon is 2.5. So there will be a polarization of that bond to itself, polarizing it towards oxygen. But because as you polarize towards this oxygen, you are also polarizing towards the opposite oxygen. As a result of that, the individual bond polarity cancel out each other. So the net dipole moment of CO2 is 0. And that is the reason why CO2 is gas at room temperature, because CO2 is not a polar compound. It is not a polar compound, so it is gaseous at room temperature. But let's look at water. In the case of water, you have water to be a bent molecule, a V-shaped molecule. Now, because it is bent, it is V-shaped, it has a dipole moment that the overall dipole moment did not cancel themselves out. Why? If you look at the molecule of water, V in this state, the electronegativity of oxygen is higher than the electronegativity of hydrogen. So that means that the polarization of the bond towards oxygen. So you have polarization towards oxygen, polarization towards oxygen. So, and they are polarizing in the same direction, not in different direction. So the moment, the dipole moment of this will be a positive value. It is not equal to 0. So the geometry plays significant role in determining the dipole moment of any compound. So this molecule has an overall molecular polarity because there is no cancellation of the dipole moment as you move from one to the other. So we can predict, we can now, as an exercise, we can predict which of the following will be polar. We have ammonia, we have boron trifluoride, and we have carbonyl sulfide. Now, the first thing we need to do is to draw their molecular, geometry. Now, if you look at starting with ammonia, ammonia has higher electronegativity with nitrogen and lower electronegativity for the hydrogen. So this is the molecular structure of ammonia. It is a trigonal pyramidal. It's a trigonal pyramidal because it's a distorted tetrahedra. Nitrogen undergo sp3 hybridization, supposed to be tetrahedral, but there is a lone pair of electron, and that lone pair of electron would will make it to be a trigonal pyramidal. Now, if you look at the implication, nitrogen is the central atom that is electronegative, more electronegative than hydrogen. So it is pulling the electron to itself, pulling the electron to itself. And because it's pulling the electrons to itself in the same direction, not in counter direction to each other, then the overall molecular polarity is towards the nitrogen and is not countered. So as a result of that, ammonia will have an overall polar molecular polarity. And that is the reason why ammonia is polar and is soluble in water. And so we can now look at another one, which is the second molecule. We have boron trifluoride. Boron trifluoride is formed by an sp2 hybridization. In sp2 hybridization, you have a dipole moment, a trigonal planar structure, And being that it is trigonal planar structure, you have your molecule, this is the central atom, then you have your fluorine in the axis of a trigonal planar structure. Now, the fluorine has higher electronegativity than boron. So as a result of that, you have electronegativity, you have polarity towards the electronegative atom. So you have the polarization of the bond towards fluorine, polarization of the bond towards fluorine, polarization of the bond towards fluorine. You will see that all these are in opposite direction. As this is pulling this, then pulling that and pulling that, they counter each other. So they nullify each other and makes the molecular polarity of boron to be 0. So the dipole moment of boron will be 0. And as a result of that, boron, sorry, not boron, of boron, I mean, trifluoride is 0. So because of that, boron trifluoride is a non-polar substance. Boron trifluoride is a non-polar substance. Now, for carbonyl sulfide, in carbonyl sulfide, the molecule is just like CO2. It's a linear molecule. Just like CO2 is a linear molecule. It's formed from an sp hybridization, and you have your sulfur and oxygen as your terminal atom, while carbon is the central atom. Now, sulfur and oxygen are of higher, oxygen is of higher polarity than carbon, but sulfur is of similar polarity with carbon. So carbon and sulfur has the same electronegativity, so 2.5, while oxygen has higher electronegativity. So because of that, you have a polarization of the bond towards oxygen and an induced polarization of sulfur towards carbon. Induced in the sense that this is polarized towards that, and this are of the same electronegativity. So you have an induced polarization towards carbon. So that ends the first, the notes that we've just talked about. I will go to the new concept that is as a result of polarity that we've talked about, as a result of the shape of the molecule. We would go and, in this current class, look at intermolecular forces. So that is the topic for today, the main topic for today. We want to look at intermolecular forces. Under these, we'll be looking at dipole moment. We'll be looking at dispersion force, the two of them being van der Waals force. Then we'll look at hydrogen bond. So we'll look at van der Waals forces, dipole interaction, dipole moments, then dispersion forces, and we'll look at hydrogen bonds. Now, so study query. Imagine you being given sodium chloride and you are given camphor. Sodium chloride will dissolve in water, but camphor will not. Why? There must be a reason. The two of them are both solids. The two of them are even white in color, but sodium chloride will dissolve in water and camphor will not. Why are some substances gas or gases and some substances are liquid at room temperature? For instance, methane is gas at room temperature. CO2 is gas at room temperature, but water is liquid at room temperature. What gives metals the ability to conduct electricity, and what makes non-metals to be brittle and not being able to conduct electricity? What gives metal the strong ability and the like? All these are the answers are in intermolecular forces. Intermolecular forces. These are between one molecule or the other, or one ion or the other. So intermolecular forces that we'll be looking at is not within the molecule, it's not intra. We have intramolecular, all that we've been learning since, where we talked about covalent bond, dative covalent bond, and even ionic bond, are within the molecule or ion. So those are intra forces, intramolecular forces. But we have the intermolecular between one molecule and the other molecule. So we have looked at intermolecular bonds, which is ionic bond, covalent bond, coordinate bond. These are interactions that hold atoms together in either a molecule or in an ion or ionic compound. But intermolecular forces is between one molecule and the other molecule. So it's not within the molecule. The molecule is already formed by the bonds, but between one molecule and the other molecule, there are forces that we refer to as intermolecular forces. These forces can be either partial ionic, dipole moments, hydrogen bond, London dispersion force, and covalent network solid or metallic bond. So we'll look at them one after the other. Intermolecular forces, which we are going to be looking at, we'll start and look at them one after the other. So the forces with which molecules attract each other are called intermolecular forces. One particle of molecule attracted to another particle of molecule are called the intermolecular forces. These forces are weak. They are weaker than ionic bonds. They are weaker than covalent bonds. They are not really bonds. They are not holding the molecules together in a bond. They are only attractions. They are only forces. So they are weak. Intermolecular forces are responsible for the physical state of a compound, whether it is going to be liquid, it's going to be solid, it's going to be gaseous. They are also responsible for the solubility of substances, whether the substance will be soluble in water, soluble in organic solvent, and the likes. It is dependent on intermolecular forces. So Van der Waals force is, or Van der Waals forces is the very first type of intermolecular forces. Van der Waals forces are weak. They are the weakest form of attraction between molecules. They are caused by instantaneous fluctuation in the particle size. If I may expand this for you to see this very well, you have molecules, you have these molecules, and they have instantaneous, or you have fluctuation in the dipole. So there is like a charge separation, and that charge separation between one molecule and the other molecule creates that Van der Waals interaction. This Van der Waals interaction is not really a strong interaction. It is just induced by the presence of another molecule. So one molecule has the positive charge separated towards one side, and the other molecule has negative charge separated to the other side, and they then have an interaction between them. This interaction was proposed by Van der Waals. Now, the other intermolecular force we'll be looking at is the dipole. Dipole, that's a polarization of any bond. Now, when you have an electronegative atom attached to a less electronegative atom, the electronegative atom will, because it's electron loving, will pull the electron towards itself. As a result of that, the electronegative atom becomes partially negative, while the less electronegative atom becomes partially positive. As a result of that, you have a dipole moment, which we talked about in the previous note. That dipole moment can then interact with one another. So you can have a dipole-dipole interaction. In a dipole-dipole interaction, there is an attraction between the partially negative of one atom and the partially positive of the other atom. So it becomes like an electrostatic interaction. It's not a bond, but an interaction. So dipole-dipole attractions are the attractive forces between a permanent dipole of two polar molecules. So there is a polarization of the bond to give you a partially positive part and a polarization of the bond to give you a partially negative part. And those two charges would then interact in what we call the dipole-dipole moment or dipole-dipole interaction. For example, in acetone, this is acetone, you have this oxygen polarizing the bond towards itself. And because it polarizes this bond towards itself, it creates a partially positive, partially negative, because it's electron loving, it creates a partially negative force, here, and you have a partially positive position here. That partial negative and partial positive between one molecule and the other molecule would then attract to each other. So you have the partial negative of this attracted to the partial positive of that, and that will create an interaction. This interaction is stronger than the interaction in van der Waals force. And because it is stronger than the interaction in van der Waals force, it increases the melting point, it increases the boiling point, because you have strong interaction between the two of them. And it also makes this molecule, this type of molecule that have dipole-dipole moment, that has polarization of the bond, to be called polar compounds, and it affects their solubility. So polar compounds will dissolve in polar solvent. Polar compound will dissolve in polar solvent because of the dipole-dipole moment. This attractive force caused by permanent dipole is stronger than van der Waals force, as I've initially explained. Then you have what we call the ionic dipole-dipole interaction. In this case, it is existing in molecules that can separate into charges. Molecules like hydrogen chloride. When hydrogen chloride can be polarized, chlorine being a highly electronegative atom, hydrogen being a less electronegative atom. So chlorine will polarize the bond to give us a dipole-dipole situation. Now, this happens in both ionic and polar bonds. So because of the fact that hydrogen chloride can even dissociate into what we call ionic compounds. So molecules are attracted to each other in a compound by these positive and negative charges. So you have what we call ionic dipole attraction. Then there is a London dispersion force. The London forces, also called the London dispersion forces. Now, these forces exist in non-polar molecules. They exist in non-polar molecules. They do not have polarization of their bond like you have in the case of polar molecule. However, they can have a dispersion force. So such force is very weak, is not strong enough to hold the molecule so strongly. So because of that, they will have low melting point, low boiling point. They are non-polar, so they will dissolve non-polar solvent. So because of that, it is possible for you to have, because of this London dispersion force, it is possible for you to have nonpolar compounds that are solid or they are liquid in nature. One would have thought that because the force is not strong enough, or there is no strong force, that all nonpolar substances will have been gases. But that is not the case because of the London dispersion force. So the London force is named after Fritz London, and sometimes it's also called the Van der Waal force. London forces are due to small dipole that exist in non-polar molecules. So because electrons are moving, they are moving randomly, so they can instantaneously form, become charged, and there will be charge segregation, and you have the, so you see that you have an instantaneous dipole. It just instantaneously happened. Then you can also have an induced dipole. You can have, once you have um, a molecule or an atom that can induce, that is relatively negative, coming close to the environment of a non-polar substance, you can have an induced dipole. So a dipole moment or a dipole form in one atom or molecule, inducing a dipole in the other, where the instantaneous is eventual electron movement, creating a tiny dipole form. Having established that, we want to quickly look at what happens in hydrogen bonding. Hydrogen bonding exists when you have hydrogen attached to electronegative elements such as nitrogen, oxygen, and fluorine. It is a special type of permanent dipole-dipole moment that is very strong. And that is the reason why we use the word bonding for it. It's an intermolecular force of attraction, but it is, the word bonding is used for it because of that strength that it possesses. Hydrogen bond is the attraction between hydrogen molecule, hydrogen atom in a molecule. When it is attached to an electronegative element, when it's attached to an electronegative element such as nitrogen, oxygen, and phosphorus. Hydrogen bonding occurs in molecule where hydrogen is covalently bonded to a very electronegative element with lone pairs. And that is very key because hydrogen can be attached to carbon and it will not have hydrogen bonding because carbon does not always exhibit lone pair. And that is the reason why we specify that it must be nitrogen, oxygen, and phosphorus, because those ones, they possess lone pairs. So the high electronegativity of nitrogen, the high electronegativity of oxygen, the high electronegativity of fluorine in hydrogen bond with them. So which means nitrogen, hydrogen, oxygen, hydrogen, fluorine, hydrogen bonds will cause you to have like 5 times a dipole-dipole moment than the normal dipole-dipole moment. And as a result of that, you have a formation of hydrogen bond. Now, this is an example of what we're talking about. You have, in the case of water now, water has oxygen as a central atom and 2 atoms of hydrogen attached to it, bonded to it. The oxygen molecule, the oxygen atom polarizes the bond towards itself because it's electronegative, then you have a partially electronegative. The hydrogen atom becomes partially electropositive. Now, there will now be an orientation of the hydrogen of another molecule towards the oxygen of another molecule that is partially negative. The hydrogen that is partially positive will orient themselves. So this will now establish a bond that is called hydrogen bond between the oxygen of one molecule and the hydrogen of the other molecule. And this is responsible for the very high melting point, the very high boiling point, and the very strong solubility of hydrogen in nature. So let's quickly recall and probably look at some very key issue. Now, all atoms or an atom or an ion electronegativity is the ability of it to pull electron towards itself. And we know that it increases as we move across the period and decreases down the group. As a result of that, these three atoms, nitrogen, oxygen, and fluorine, are about the atoms with high electronegativity. Then, because we are increasing electronegativity across the period, then we are reducing it down the group. So because of that principle, those two elements are common when we are forming hydrogen bond. It's common with nitrogen, oxygen, and fluorine. Those are the elements that always form hydrogen bonds. So hydrogen bonds are stronger or are the strongest out of all the intermolecular forces. Hydrogen bond is possible because in hydrogen atom, there is no shielding of the nucleus, no shielding effect. Then hydrogen bond is responsible for so many fantastic things. For instance, hydrogen bond is responsible for biological activities where we have protein in the human system, carbohydrate in the biological system, carbohydrates in the biological system, protein in the biological system. They interact based on hydrogen bonding. You have formation of hydrogen bond in amino acid to give what we call the DNA in living system. It's also responsible for the value of water, the importance of water, and the usefulness of water. It is responsible for the high melting point, the high boiling point of molecules. If you compare, for example, water and methane, methane does not have hydrogen bond. Water has hydrogen bond. If you look at carbon dioxide too, carbon dioxide does not have hydrogen bond. Water has hydrogen bond. Um, Carbon dioxide is equally not polar. Water is polar. If you look at the mass of carbon dioxide, you have a total of 44. And if you look at the mass of water, a total of 18. Water is of lower atomic mass than carbon dioxide, but water is a liquid at room temperature, and carbon dioxide is gas at room temperature. It's hydrogen bond that is responsible for that high melting point and high boiling point. The reason why methane does not have hydrogen bond is because carbon is not too much electronegative mean, the distance between electronegativity of carbon and that of hydrogen is not that much. So the electronegativity of carbon is virtually the same as the electronegativity of water. I'm sorry, the electronegativity of hydrogen. So because of that, there is no polarization of the bond. Now, but in ammonia, there is hydrogen bond. One, because of the lone pair, because we have said that lone pair of electron on the central atom that hydrogen is attached to play a role in hydrogen bond. Then nitrogen is more electronegative than hydrogen. So there's a polarization of the bond. And as you polarize the bond, the lone pair of electron is also contributing a role. So nitrogen is very electronegative. It has one low pair of electron that you have in ammonia. And as a result of that, you have hydrogen bond in ammonia. Also in water, you have hydrogen bond in water because there are two lone pairs of electron on oxygen, and oxygen is more electronegative than hydrogen. So you have a polarization of the bond towards oxygen in the two bonds. And as a result of that, and the fact that there is no cancellation of the dipole moment, you have that occurring. So how do we, what do we bring out of all this? Hydrogen bonds attached directly to one of, hydrogen attached directly to one of the electronegative atom. The electronegative atom polarizes the electron to itself and becomes partially negative with the lone pair playing a role. Then you can, so you have the three lone pairs here, two lone pairs here, a lone pair here. You have a partially negative, partially positive, partially negative, partially positive, partially negative, partially positive. And then interaction between them to each other, between one molecule to the other molecule, cause what we call the hydrogen bond. Very quickly, the hydrogen bond then play a role in what we call water chemistry. It is one of the reasons why water has both cohesive and adhesive force. Water has cohesive force, which is the ability to stick to other water molecules. So the hydrogen bond makes water to be able to stick to other water molecule. So you have cohesion. Then adhesion is the ability of water to stick to the wall, to stick to the wall, or to stick to other polar molecules, to stick to the wall of the container, or to stick to other polar molecule is also caused by hydrogen bond. So properties of water, it has high specific heat capacity, high melting point, high boiling point. So that is a large amount of energy is required to change the temperature of water. Then it also has high heat of vaporization. When you evaporate water from the surface, that evaporation will cause cooling at that surface. So there is what is called evaporation cause cooling when you evaporate water. Then you have solid water is less dense than liquid water. It is called the anomalous behavior of water. Between 0 and 4, you have the the water becoming very dense. So 0 and -4. Between 0 and -4, you have water having the highest or higher density. So because of that, ice will float on water. Ice will float on water. So bodies of water freezes from the top down because of the density of solid water over liquid water that is less. So you have solid water floating, and that is also caused by hydrogen bond. Then it is also hydrogen bond that makes water a very good solvent. Water dissolves virtually all polar molecule and all ions because of that presence of hydrogen bond. It gives water a very strong ability to dissolve or to hydrate and solvate ionic bonds, and also to dissolve polar compounds. Then water also organizes around non-polar molecule. So you have what we call hydrophobic and hydrophilic molecule. Phobic, fear. Philia, love. So hydrophilic means water loving. Hydrophobic means water hating. So water causes hydrophobic molecule to aggregate and assume specific shape. Water causes hydrophobic molecule to aggregate and assume specific shape. Then another thing with water is that it can dissociate into, despite the fact that we specify that this molecule, it can dissociate into ions. You have hydroxyl ion and hydrogen ion. Then it can also act, it can be amphiprotic, meaning that it can interact, you can have two water molecules giving you hydronium ion and hydroxyl ion, in which water is acting as if it is an acid or a base to each other. That example is not on the slide, but it's also amphiprotic. Then you have this property of water. This property of water has a lot of physical and biological effects. So most property that water display is as a result of the interaction that different molecule of water has on each other. So water is cohesive, it attracts to itself. The higher the cohesion of water, the high cohesion of water is a reason why you have surface tension. Because water pulls themselves towards each other. When you have water in a container, you will see the surface tension. Water would have a meniscus that is curved towards each other because it has that strong cohesive force, strong attraction to other water molecule. Water has high boiling points. We've talked about that, so I will not necessarily stress that again. Then the bonding of hydrogen is what binds peptides together, what binds strands of protein together in a DNA, and is responsible for biological life. So hydrogen bond is responsible for biological life. So what hydrogen bond does is that it holds the DNA double helix together. It holds polypeptide together in what is called a secondary structure of protein. There are three structures of protein: four: primary, secondary, tertiary, and quaternary. So it's hydrogen bond that makes that to exist, that makes that to happen. Then it's also enzyme to bind to substrate. Enzymes are catalysts that catalyzes biological reactions. And in the course of catalyzing biological reactions, it's bind to substrates. So it helps enzyme to bind to substrate. It helps antibodies to bind to antigens. Antibodies are also proteins that are in human system. So to bind to antigens, it is through hydrogen bond. Then it helps transcription factor binds to each other and to DNA. So this is a question that I will post on the, I will pose this question on Pladis for you to respond to before the next class. So summarily, you have different types of intermolecular forces. You have the van der Waal, you have the dipole-dipole, you have the hydrogen bond, and you have the ionic bond. There are specific examples of compounds with each of these. The weakest of them all is the van der Waal force. The strongest of them all is the ionic bonds and the like of that. So physical properties such as boiling point, they are dependent on the strength of the intermolecular force. So boiling point of a compound is the temperature at which the molecule is converted to gas. It is also expressed as the temperature at which the vapor pressure is equal to the atmospheric pressure. And a compound will boil when your energy that is introduced into the system overpowers the intermolecular force of attraction. So when the energy overcomes the intermolecular force of attraction, you have the molecule, you have the molecule separated and you have your compound melting or boiling, and as the case may be. So the stronger the intermolecular force of attraction, the higher the boiling point. So if you look at it, you have van der Waal that is the weakest, you have dipole-dipole moment, you have hydrogen bond. So you have increase in strength and increase in the boiling point. Ionic bonds, ionic compounds are held by electrostatic force of attraction, and because of that, they have very high melting and boiling point. Covalent compound, on the other hand, has lower melting point, but their melting and boiling point is dependent on the intermolecular force of attraction between them. Also, we've talked about solubility. In solubility, like dissolves like. So polar substances will dissolve in polar compound. Non-polar substances will dissolve in non-polar compound. Water is polar, so it will not dissolve most of the organic solvents, but organic solvents will dissolve most of the organic compounds. So, for instance, carbon trichloride is not polar because of the negation. Hexane is not polar. Ethers are not polar. All these will dissolve in organic solvent. But acetone, ethanol that has hydrogen bond, they will dissolve in polar substances or polar solvent, and in particular water. So the polar substances will not dissolve in non-polar solvent. Non-polar substances will not dissolve in polar solvent. Like will only dissolve like. The last intermolecular force that we're going to look at is the metallic bond. The metallic bond exists between metal ions or metal atoms, and you have, even in alloys of more than one or two metals, it also exists in them. And metallic bond exists because of electron C. In each of the metal particle, there is an electron C that is created, and that electron C creates an movement of electron around the particles of the atom. And that electron C is responsible for you have a close pack cation of all of the metals, and you now have electron moving all around. So electron C or electron band, and it depends on the number of valence electrons. So metal atom gives up their valence electron to form this electron C, electron band, whatever. And they release electron, they move freely in the metal. Because of that, they give metal the ability to conduct electricity, the ability to conduct heat, the very strong bond that makes it to have high melting and boiling point. And in some cases, they give it even the lustre nature, the ability to shine, like you can see in the case of gold. So you have good ability to conduct electricity because of the free electron. They are malleable and ductile because of those electrons that is binding them together. So not in rigid position. So iron can be shaped, can be drawn into wire and the like. Then they can conduct it also because of the free electron. Then they can be shining, so they look lustrous. They can absorb light and shine. Then the electron act as lubricants. They act as lubricants, causing cation to move easily past each other. So they slide on each other. And when you have a mixture like you have in alloys, the mixture of two or more metals, you can also have that interaction. So it made by melting of metals together, then it may contain in some cases non-metals, and you have this as some of the alloys. And alloys, when you see that you have like 1, 2, 3 different metals. You have, though this is metal and non-metal, and the like of that. So this is a convenient point for us to stop the class. I may not be able to take questions because we have very limited opportunity to discuss. So we would meet next week as we continue the class. Thank you and God bless.